Welcome back to day 2 of our AP review. Yesterday we were talking about topic number 1. We were going through some of the early stuff of chemistry, the electron configurations and such. And today we are moving into their topic number 2. With topic number 2, a quick reminder of our topics here. So we were doing atomic structure and properties last time. Today we will be working on number 2 here. We were looking at molecular and ionic structure and their properties, which for us was mostly Unit 9. However, we did talk about a little bit of this with regards to Unit number 11. We talked about some of the metallic bonds and a little bit of the network covalent bonds falls in the Unit 11, and so we'll want to address those a little bit as well. So let's come and take a look at our cheat sheet that we're creating here. We know that yesterday we were trying to put most of our notes and information in the area where the reference table was. However, for this particular unit, this section, there's not really any given information on this reference sheet here. So you'll probably just want to take a few notes on a separate sheet of paper and staple it to this so that it's all in one spot. So really what we called Unit 2, what they're calling Unit 2 is what we called Unit 9. It was mostly bonding. So when we're looking at this bonding unit here, let me just move this up a little bit here. So that's what we're going to call bonding. So this is going to be the different types of bonds and all of that stuff. When you open up this unit, this topic that they're discussing here, what they break it down into is several things. They are going to be talking about, let me switch my thing here. They're talking about chemical bonds. They are talking about the structure of solids. They're talking about metals. They're talking about Lewis dot structures. Lewis dot structures, resonance. They are talking about formal charge. And hybridization. And finally, VSEPR. So this is quite a unit here, but you'll notice that all of these different things that we're looking at, none of them really have any formulas. So a couple of things that I wanted to hit on. First, we'll sort of take a quick look at the different types of chemical bonds. And with regards to chemical bonds, we're talking about the intra. These are the intramolecular forces. So these are ionic bonds, covalent bonds, and metallic bonds. So when it comes to these types of bonds, you should recognize that, for the most part, many of them are forming crystals. You should know which ones are and which ones don't. And really what they focus a lot on are some of the properties. The properties they focus on oftentimes are melting point and conductivity. So with ionic bonds, the melting point, let's just turn this into a chart here. With ionic bonds, the melting point is generally very high, right? These are very strong bonds, and in order to break apart something like NaCl lattice, you're literally having to break ionic bonds in order for this to melt. The conductivity, only when aqueous or liquid. Liquid would imply that you've melted it. Covalent, the melting point is usually low, and the reason for this is because when you go to melt a covalent compound, you're usually not breaking the covalent bonds, but there's generally some type of intermolecular force, like hydrogen bonding or something, that you could break in order to melt ice or something along those lines. So it usually melts pretty easy, and the conductivity would be never. And then metallic bonds, generally we see high melting points, but not always. There are always exceptions here. And then the conductivity would be always. Now, one other one that we probably should throw in here, and that would be network covalent. We don't want to forget about those. So maybe I should have probably made better space here. Let's do this. Let's scoot this over and we'll shrink it down a little bit to see if we could get the network covalent to fit in over here. So we'll go net. So with the network covalent, typically the melting point is high because you have to break covalent bonds now in order to get the thing to melt. There's not really a lot of intermolecular force here. And then the conductivity is usually never. I say usually because remember, there is one sort of exception to some of these network covalents, and well, let's go with never. But understand that there is graphite. Graphite can conduct electricity, and we talked about some reasons why. But a lot of times they won't classify graphite as a network covalent. They'll still with the diamond, they'll keep it as a network covalent. But a lot of times the graphite, because of those hydrogen bondings between sheets, they won't classify it that way. So that one's kind of iffy, but most of the time they're just referring to things like diamonds and that type of deal. So these are some different traits and characteristics that we should know for those. So that takes care of our chemical bonds and structure of solids. Remember metals, a key thing to metals, sea of electrons. Remember that those electrons are floating and flowing, and they give rise to all of their interesting, crazy, and unique properties. And so that's probably going to pop up at some point, I would guess. I mean, it used to always be like a multiple choice question or something. Now, as far as these last ones that we have here, the Lewis, resonance, formal charge, hybridization, and VSEPR, this is more of a drawing type of thing, so it might be easiest to review those just doing a couple of quick drawings. What is this? Let me just move this down and out of the way here. Make some space. So we've got, for a drawing, let's just do a really common chemical that sort of covers a lot of bases. Let's go ahead and do something like CO3 2-. And the reason I'm picking this one is because really it does cover a lot of things like resonance and formal charge and such. So when we're looking at these things, remember that the best, most consistent way is not to just connect the dots. It's something where you want to actually think about the valence. So carbon has 4 valence, oxygen has 6, and there's 3 of them. And then there's 2 additional electrons there. And so this gives us a total of 24 electrons that we have to work with. And so what we would do is we would go ahead and take our central atom, so the carbon, and we're going to surround it with the oxygens. And now we're thinking of VSEPR. We know that the electrons and the bonds are going to repel, and so we're trying to give them as much space as we possibly can, as much room. And so this bond angle is probably going to be best for us there. We'll talk about that in a second. Next thing we want to do is start assigning our electrons to the outer ones. So usually those are the most electronegative elements. They're going to want to get the most electrons, so we're going to go ahead and put them on. So we're going to give them all their octet. Just putting in our octet here. And then so now we have 8 times 3 is 24. We've got the right numbers on here. But we want to take a look at our formal charges. So formal charge, what you do is you look at the periodic table and you see, what does carbon usually have for valence? Well, it usually has 4 valence electrons. So normally has 4. And what does it have now? Well, in this bond right here, it has 1, and then the other one belongs to oxygen. And in this bond, it has 1. The other one belongs to oxygen, 1 and 1. So right now, carbon only has 3. So it has a formal charge of positive 1. When we look at the oxygens, they have 1, 2, 3, 4, 5, 6, and then 1 in the bond is 7. Normally, oxygen has 6. 6 minus 7 is a negative 1. So these are all negative 1s. And in the end, this entire thing is supposed to add up to a negative 2, which is what it's doing. We have a negative 3 plus a 1 takes us to negative 2. However, are these the best formal charges possible? Well, we could see the carbon doesn't have its octet, so it's not going to be the greatest, right? When we see things that don't have their octet, that's a bad sign. The carbon is a fairly electronegative element. It's pretty high up on the periodic table, and it's pretty far to the right. It wants to gain electrons. It doesn't necessarily want to lose them. We know that it tends to form covalent bonds. It's usually sharing, right? It's not forming positive ions. So what's a better way of doing this? So what you would want to do is take the next step, and you want to get better formal charges on this. So when you see something that does not have its octet, you want to move some electrons around. So we're going to draw this again. And we're going to go ahead and put the oxygens down. We're going to go ahead and put all their dots back in. So I'm just kind of restarting where I was up above. And so this is my structure so far. It's a -2. And I wish I hadn't drawn that so big. It's kind of making a mess of things. All right, so we've got our structure here. And what we're going to do now is we're going to remove 2 electrons from that top oxygen, and we're going to turn them into a bond. So now when we find our formal charges, the carbon has 1, 2, 3, 4. So it was 4 originally, -4. Now it has a formal charge of 0. That is ideal. You want them to have formal charges of 0, if at all possible. The oxygen had 6 in the beginning. How many does it have now? 1, 2, 3, 4. And then 1 there and 1 there is 6. It's got a formal charge of 0. And then down below, they had 6, and now it has 1, 2, 3, 4, 5, 6, and 7. And those are equal to -1, which it's got to happen because we added 2 electrons on. But this is not a bad thing because oxygen is more electronegative than carbon. If anybody's going to have it, it's going to be the more electronegative element. Now, when I did this, I chose to give the double bond to the oxygen up top. But did I need to do that? Well, I could have assigned this lower oxygen to have it. Okay? This is something that we have to pay attention to. Sometimes we get in these situations where you have options. And I picked the lower left this time. Should I have picked the lower left? Well, I could have also picked the lower right. And we could have had a structure that looks like this. So which one of these is correct? Well, they're all correct. They're all actually happening at the same time. This bond is delocalized. It's resonating. It's moving. So in one instance, we would see this structure appearing. And then you'd blink your eyes and the double bond would have flipped to over here. And then you blink your eyes and it would have flipped to over here. And then it's back up here. And then it's here. And then it's here. And what it really does is it averages out to something in between this. And so we would say that the bond order for this, if you don't remember bond orders, this bond order would be about 0.33, right? So it's 1/3, 1/3. So when we're looking at something like this, we have the bond orders, we have our hybridization, okay? So we need to look at our hybridization. How is this thing bonding? We would say that it is got to get the pen back, SP. We've got 1 here, 1 here, and then there's a double bond here. Right? And so we have SP2. because we have an S, and then we need to do is a P and a P that are all going to blend together. Remember that this pi bond right here, so the first is always a sigma, the second is always a pi. The pi bond can't hybridize. Okay, so we're going to have something like this. All right. Let's see, what else did we need to do here? Did I say bond order? The bond order for this, I think I did, yeah, right, because we have, sometimes it's sometimes it is a double bond. So if we were looking at this, why are you doing this? Sorry guys, this has been, we have, sometimes it's a double bond, and then it's a single bond, and then it's a single bond. So it's a double bond right here, and then another bit of the time it's a single bond, another bit of the time it's single bond, and then we would divide that by 3, so we get that 1.33. I think I said that up above. Anyway, so we've got the bond order. This is what we call resonance. This was our formal charge. This is our bond order. What else did we have? Let's take a look here. Hybridization. And then the last thing we need is our bond angles, our shape, right? So if we're looking at this particular one, this one's usually pretty easy for us to see the shape. So the valence shell electron pair repulsion would be trigonal planar with angles of 120 degrees. Now, sometimes they're not going to give you something that's quite as easy as this particular one. Okay, this is back again in my way. So when we are looking at molecules, keep in mind that sometimes they're going to give us, remember they said there's no OChem on the test, but they use OChem examples all the time. What if they gave us something like this? CH3, CH2, C double bonded O, OH. And I said, what are some bond angles here? Sometimes they'll just pick an area and go, hey, what are the bond angles on that carbon? Or what are the bond angles on that carbon, or that carbon, or that oxygen, right? So we have to think back to all the different things we're doing here. So this guy right here, this very first one that we're looking at, this is a carbon with 4 bonds and no lone pairs on it. So this is going to be a tetrahedral shape. This is 109.5. The same is going to be true here, 109.5. But when we get to this one, now we only have 3 bonds. We have 2 singles and a double. So this would be 120 degrees. And then what about this last one? Now we have 4 effective pairs, right? We have 2 lone pairs and we have 2 bonds. But remember, lone pairs take up a little bit more space than a bond does. They kind of poof out like a cloud. And they're going to push those things away. And so this one is actually going to be a bent shape. And so this would be 104.5 degrees. So you might want to go through and kind of review some of your bond angles if you're not remembering those types of things. But these are typically in a molecule that they give you. These are, I would say, the 3 most common, right? In terms of a large sort of continuing chain or molecule like this. So that should cover most of it there. Hopefully these helped you guys. These little notes here helped to spur some memories, sort of review it. Remember, look back at your unit objectives, look back in those units, and let me know if any questions pop up.